Welcome back. In this lecture, we will look at how water and temperature management is crucial to proton exchange membrane fuel cell. In a previous lecture, we had looked at similar issues on water and heat management in the context of solid oxide fuel cell. There, water and heat that is generated is recycled back to improve the efficiency of solid oxide fuel cell. In the present lecture, we will look at the similar issues in the context of proton exchange membrane fuel cell. In PEMFC, hydrogen and oxygen are supplied to fuel cell to form water and an electrical output. This is the reaction on the side wherein oxygen is supplied as part of air. Oxygen reacts with proton to form water. So in a PEMFC, the hydrogen that is supplied forms proton and is conducted through the electrolyte. The conductivity of the electrolyte is very much dependent on the water content of the membrane. If the electrolyte, the membrane, if it gets dried up, the resistance of the membrane increases significantly and prevents conduction of proton. That is one extreme wherein membrane may get dried up. The other extreme is when the water that is formed is not adequately removed. If in that case, the access of oxygen to the electrode surface is blocked, therefore the mass transfer resistance due to the presence of water droplets has to be decreased to improve the access of O2 to the electrode surface, electrocatalytic surface. Here, we are going to mention the balance of water by looking at how much water gets in and how much water gets out of the system. N dot represents the flow rate of dry air. This represents the mole fraction of water vapor present in the supplied air. Therefore, the input here is given by this quantity, simple balance. And the water produced can be given by this formula. I refers to the current that is being generated. So if you look at the stoichiometry, for 1 mole of oxygen, 4 moles of electrons are utilized to form 2 moles of H2O. Therefore, water produced can be obtained by knowing the amount of current that is being generated in the fuel cell. I by 4 times 2 would be the amount of water that is being produced. Water output from the system can again be obtained from the stoichiometry. If this is the amount of input air, some amount of oxygen gets utilized towards the formation of H2O. The amount of oxygen utilized can again be obtained from I, because 4 moles of electrons are utilized for every 1 mole of O2. This is the amount of oxygen that is depleted out of the airstream during the operation of the fuel cell. So once you know this, you can get the water output just knowing the mole fraction of water in the output, which can also be obtained by the logic that the air that comes out of the fuel cell is saturated with water. So if you know the temperature of the fuel cell, you can know the vapor pressure of water vapor at that particular temperature because air is saturated. So, water vapor pressure divided by total pressure will give you the mole fraction of water vapor in the output stream. The utilization of O2 can also be obtained because this is the amount of oxygen that is being consumed divided by the amount of oxygen that is fed into the system as part of air. So this is the flow rate of dry air, and the mole fraction of O2 in the dry air stream is YO2. So this is the input oxygen that is being supplied. So implementing this into the mass balance equation for water, this is the amount of water that is being supplied, amount of water that is being produced, and the amount of water that is gotten out, that gets out of the fuel cell. This is the mass balance equation. The control of temperature is crucial for because of this behavior. For a given utilization rate of oxygen, there is only a single temperature where there is optimal balance. We are not going to derive the basis for this plot. We are just going to mention this plot as an observation. What do you observe? Let's say the utilization of oxygen is, let's say, 0.4. If you're operating at higher than a particular temperature, the membrane tends to get dried out, which, as we mentioned, increases the resistivity of the membrane, preventing the transfer of protons across the membrane. Below a particular temperature, there is water flooding, and which prevents the supply of oxygen to the electrode surface. So there's a single temperature for a given utilization wherein there is no dry out as well as there is no flooding. So this is a very uh, difficult thing to such a control of temperature is not easy. So there are advanced methods for water management in proton exchange fuel cell. We are not going into the different mechanisms that are involved in water management, but what is important to understand is if you're at very high temperatures, the membrane may get dried out, but if you're lower than a particular temperature, there'll be flooding in the proton exchange fuel cell. So measurement of temperature and the control of temperature is very critical for PEMFC. In the next lecture, we will look at certain aspects of how mechanics gets coupled to the electrochemical system. That will be taken up in the next lecture. Thank you.